Thanks for the invitation to be here. I was at Berkeley a long time ago, actually, exactly 1998. I spent 1 year here after I finished my PhD, and it was really a great time. Many of the things I'm going to talk about actually started somewhere here, although by now I've took them in different directions. So the first thing is I should apologize for this very generic title. Actually, there's going to be content to this presentation. Not you'd guess from such a title, but I do have one first slide to show you a bunch of devices that somehow motivate what I'm going to talk about. And you see that in all these devices I put some price tags and sizes. And that's to emphasize that I'm interested here, and in contrast to last week's seminar, I'm interested in small devices, cheap devices that are going to be on board. Could be moving, could be UAV, something like that. So just, at top there you see a micro. By the way, none of these are particularly new devices. Perhaps the newest ones would be somewhere in the sensor. These are old established devices. That's why this microcontroller costs 39 cents, right? So you can basically put it everywhere without any price. If you want to go to something more complicated, you could get a Raspberry Pi. It's not as fast as my laptop, but maybe a third of the speed. So that's in terms of computation. In terms of communication, you have several things here. I'll talk a little bit about wired computation, but that's a CAN controller. This is a particularly interesting one, ESP8266. It costs about $2. I forgot to put the price there. The 32-bit processor, 32.11 there. You can do quite a lot with it. It's incredibly small and inexpensive. You could go for something that has a range of 45 kilometers in line of sight. Also very cheap. And in terms of sensors, there's some ideas here of what you can get. So the idea is that you can get relatively good computation and communication very cheaply, wherever you want it with no price. So I want to explore that a little bit. Now, in terms of a control system, what this means is that when you build a control system, being it a robot out in a factory, a drone, a car, you can put these things together and build sensors that are smart. You can put sophisticated computation in them. They can use general-purpose networks, so it's going to be extremely flexible in how you organize this, how you deploy them, etc. In many cases, the power consumption is so little that you put it on a AA battery, and it can last for months, if not years, if you sleep it for long enough periods of time. So we should no longer just think about these control systems where you have this unity feedback loop with all the lines are wires, but instead are going to be communication networks. Talking now about the communication, but then also remember that now we can do complex computation. So sometime not that long ago, we would explain that the reason why in undergraduate classes we teach things like proportional, integral, different PID controllers is because, well, that's the only thing you can really put in.
I don't mean to argue with you, but I have lived through this many times in a painful way. If you could kindly add to the interconnection that is local, because the moment you go through the routers outside of the campus or any other organization, you are in trouble.
You are, but I see that as a challenge. As a control engineer, I want to now figure out how to do it in spite of that, right? And I will talk a little bit about that. So now let me tell you what my talk is going to be about. There's going to be two parts to it, somewhat decoupled. One, I want to focus on this idea of networks in the middle of my control loop. This is this network control systems. So I'll address questions like the one that Regina just told us about. The second part, I want to explore the idea that you have lots of computation. You have computation to spare. Even the slowest of those microcontrollers I told you have 16 megahertz clocks going all the way to 1 gigahertz. So there's a lot you can do, much more than just multiplying a few numbers, which what a PID controller needs. And I will tell you about one particular method of control, sort of related to something called model predictive control, that we've been using. All right, so let me talk to you first about these network control systems and what happens when you have networks. This slide shows you several of the systems where now you see network control systems. My interest in this area came from actual work that started here at Berkeley, was to try to connect multi-agent systems. And of course, you're connecting systems that move, you have to have wireless communication. There's nothing you can do about it, so you need some sort of communication medium that you're going to share with everybody else. But other areas we worked on are cars, and at this moment, cars are probably some of the most sophisticated control systems or network control systems that you find in the market. At this point, even the most low-cost cars would have networks embedded in them with hundreds of elements. And in fact, in those networks, you start having issues with bandwidth. And by the way, one thing that happened when you start having this in cars is that the weight of the cars decreased just because you remove all the copper. That was a non-significant amount of weight in cars. Other things, this is the process control industry. You have lots of them because in any processing plant, you have thousands of sensors, literally thousands, probably 10,000 sensors. And they all have to talk to the controllers, and there's also building automation. So let me now address specifically what these networks have to do with control systems and why you have to worry about them. This is it's an active suspension system, right? So you have your car. This is the mechanical drawing. You have the 4 wheels. You have active suspension on all the wheels. If you want to think it from the perspective of a network, it kind of looks like this. You have a bus. Most of the times you use something called a CAN bus, or a particular real-time bus. This would be very standard. You have 6 nodes, 1 node per wheel. These nodes have both sensing and actuator at each one of the wheels. You have a controller. You have a roll and pitch angle sensor. That's 1 node. And you have a HIF position, so vertical position of the sensor. And these people that are reference sets, this is actually not a very recent paper, it's an old paper. They did a control design for this. And this is the response of the system after a bump in the road. So you have a disturbance, which is a vertical acceleration, happened right here. And you have 2 curves. Those are 2 different responses. And of course, you see that in the green case, it worked OK. The car went up and down a little bit, nothing problem. But the red is unstable, right, eventually. The 2 curves are exactly the same controller, same network, same bandwidth, same sampling times. Everything is equal, except for one thing. In CAN, you assign priorities to each node. The nodes with the lowest priority go first. So there's contention. There's actually no collision of messages. They just figured out the one that has high priority goes first. The only difference was the priorities of the messages in these nodes. So in the green curve, small numbers mean high priority. The controller had the highest priority. So when there was collision, the controller would speak, and everybody else would wait. And in this one, there was a small change. The priorities were flipped so that the 7, which was one of the wheels, actually became to have the 2. This sensor becomes to have the highest priority, and the controller had the lowest priority. And the difference was the difference between stability and instability. I should add that for this sampling time, there was capacity in the network for the system. No messages were being dropped in any of the simulations. It was just the fact that in one simulation, the waiting times of the messages were different from the other. So what this shows is that it's not enough just to design a control ignoring the network, because if you implement it this way, it works. If you implement it that way, it doesn't work. Right? So the idea here is that we have to somehow take this into account. There's one thing I should add, though. This doesn't actually happen in real cars. The way car manufacturers protect against this is, even though this network, the CAN bus is limited to 1 megabit per second, the first thing they do is they only use it at 125 kilobits per second just because of electromagnetic noise. But then they only use it typically at 25% capacity. So they are so below capacity that you never have to wait. However, 1 megabit is not that much. And in fact, in trucks, CAN no longer works, and they have to do all sorts of weird stuff. So as you put more stuff in this network, this becomes a bottleneck. All right. So let me tell you a little bit about things that can be done now in this context. And the first thing is that if standard techniques don't work, we need different models to analyze these systems. And I'm going to tell you about one particular model. It's called Stochastic Hybrid Systems. And then I'm going to tell you about one particular result. OK, so this is one feedback loop where instead of I show you the system with a car at 7 nodes. This one I simplified my life. I just put there's really only 2 sensors here and 1 controller. And the 2 sensors talk to the controllers through a network. And so they have this network here. There's measurements. The 2 sensors measure. They send to the network. They measure this Y1 and Y2. They send a message to the network. And they have, on this side, you have some hold devices. Whenever you get a measurement from sensor 1, you hold that value and you keep it constant. Then you receive a message from sensor 2. You hold it here. And the idea is that sort of this network hopefully is somewhat transparent. It's like as if sensor 1 is connected to this line here, this y hat, y1 replicates y1, etc. And I'm going to consider here the simplest algorithm you could imagine, which would be a round robin. So you're going to sample this, sample sensor 1, sensor 2. You send them in an alternate fashion. So what will this look like in terms of a model? Let's assume that's a linear system. So we have standard equations. This is the input. This is the output of the process. You have some controller. The controller, notice that the plant produces Y, the true output. The controller, well, it doesn't quite have Y, so it has to use this Y hat. This, by the way, is wrong. This should be U. The controller produces U, not Y hat. Sorry about that. And then there's a little bit more going on, right? Then I have to think about these holds. And these holds are sort of easy to model. At least most of the time, they're just constant, right? Just holding. So derivative is equal to 0. With the caveat that when messages arrive, you have to update the hold. And that this equation here. So for odd instance of time, you get the state of the hold. Actually, see this y hat is now connected to the y1. So you receive this measurement at odd instant of time. The other one, at odd instant of time, just y hat remains the same as the y hat. All right? So that's what, then at even instant of time, this thing flips. All right. So this is relatively straightforward. Now, let's imagine the situation. What happens is, so the interesting having a shared network is that you're sharing the network with other stuff. Right? If you just do a network just for this, then you don't really gain much. You still have to put the wires there. But you're sharing a network. And so it may happen that at some points, when you try to send a message, the network is busy, and you're going to have to wait. What's going to happen is that, well, you wait. In the case of the CAN bus, you know exactly when the network becomes free. And then you're only going to send your measurement then. And there's a couple of possibilities here. One of them is you wait, you keep this measurement you took in a buffer, and then you send that measurement. So you send the old measurement. But there's really no reason to do that. You might as well, when the network is free, just do an analog to digital conversion and send the latest measurement. What's happened, kind of no matter how you do it, is that the times at which these holds are updated are not going to be fixed anymore. Even if you try to sample this at a constant rate, the time at which these are updated is going to vary. Right? We're going to, most of the time, is going to have the same value, which is going to maybe sampling at 1 millisecond. But occasionally, there's these collisions, and occasionally, you're going to have to wait longer. So I'm interested here in studying a system which is going to have sampling, which is going to be variable. By the way, these equations here, I should have said that this is kind of assuming there's no delays on the network, right? Because I'm saying that the y1 at a tk is equal to the y1, so there's no delay. There's actually ways to model delay. Generally, what you do to model delay is you create extra states, which are the packets on route. right? You just store that. This is the measure that are going through the network. That's a simple way to introduce delay that doesn't force you to deviate from this particular formalism. Okay, so now I have variable intersampling times. And there's two options here for that. One is a deterministic. So that would mean I look at this network, I observe what happens for a large interval of time, I figure out what's the smallest intersampling time, the largest intersampling time, and then I want to design my system to make sure that for any samples in this interval, the system is going to be stable. If you do this, what you're going to find, this actually seems very simple, but in practice very complicated. So I also did work on this modeling, and I'll tell you what's the first thing. You actually leave one of these networks running for a day. What you're going to find is in the period of a day, this number is going to be crazy, because there's going to be one time that someone turned on a fridge, and for a couple of minutes, or a couple of seconds, nothing arrived. Now, people are not always turning on the fridges at all the time, but if I'm going to follow this approach, what do I put here? Do I just throw away this? Most of the time is at, let's say, 30 milliseconds, but there was once during these 8 hours that this was 2 seconds. Do I design a control system that handles any sampling time up to 2 seconds? If I try to do that, I will not get a good control system at all, right? It's complicated. The other one, and this is what I'm going to pursue here, is to try to look at these intersampling times as random variables. And though I do the same experiment as I was telling you before, I observe this over a day, but instead of just getting the min and the max, I look at the histogram, right? And now I got some distribution. Let's assume that they were independent to simplify my life. And I would like to then make sure that the system behaves well in some sort of probabilistic sense, maybe a expected value being bounded or something like that. This is what I'm going to do for the reasons I already mentioned. It is, however, interesting to think about what this distribution is going to look like, because unfortunately, it's not going to be a simple standard distribution. Think about where this is coming from. So most of the time, so I'm sampling, suppose my sensors would like to sample every 1 millisecond. With high probability, I'm actually going to get 1 millisecond, because with high probability, there's not going to be collisions. But then occasionally I get collisions. And when there's collisions, often I have to wait a little time. Maybe my protocol even says, wait for a uniform distributed amount of time. What this leads is to distributions that look like this. Maybe this is your regular sample time, maybe just a little bit of variance because your clocks are not quite right. And then when there's collisions, you may have a multimodal. So thing to note is that it's not going to be, for example, Markovian, which would simplify our lives tremendously. They're going to be typically complicated distributions that in fact also depend on what the protocol is doing when you have collisions. Okay, so I told you I'm going to do stochastic model. This is going to lead to something called stochastic hybrid systems, which I'm going to introduce next. It's in fact one of the first papers that introduced this terminology, stochastic hybrid systems, was from Berkeley in around 2000. So for this audience, probably I don't have to say too much about what an hybrid system is, but I'll put here just a plot. This is still not stochastic, because actually there's lots of ways to introduce stochasticity here. But this would be a representation, we're going to call it an automaton type representation. So the way to look at this plot is you say that this system has 3 modes. Each one of those circles is a mode. If you start, for example, on that mode there, you say I'm in mode number 1. And you have this continuous variable that evolves according to this differential equation, x dot equals f of 1 of x. Then you could stay there forever, but perhaps at some point, a condition becomes true that allows you to jump, or that there's no non-determinism here. So if at some point this function g1 of x becomes positive, 0 or positive, then you say there's a jump, you go to the second mode, and from that point forth, you'd have another equation, could be that x dot. And maybe you stay there forever, or maybe not, because if there's another condition there, if g2 of x ever becomes larger or equal than 0, you jump to another mode. So this is the idea one could, there's some terminology there that maybe you know. This condition is called guards. You have this reset map. So I didn't say that. in this particular model, that's going to be important for us. When you jump to a different mode, not only the differential equation, you go from x dot equals f1 to x dot equals f2, but you may have instantaneous changes on the state. So the state just suffers an instantaneous discontinuity, and I'm going to need that. There's many ways to introduce stochasticity here. Two basic classes. One is we call time-triggered, one I'm talking about here, and I'll show you later an event-triggered one. But in time-trigger is simple. Instead of having these conditions, these card conditions, you have some random variables which are going to determine when you jump. Right? So this T1, whenever you get a T1, you jump from 1 to 2. When you get T2, you jump from 2 to 3. When you get T3 to 1, it's a very simple one. There's just a circle, so it's very simple. And then these random variables, the difference between consecutive of these times follow a distribution that you know. Right? There's lots of complications to be made here. For the purpose of the system I'm going to show you, I don't need anything more complicated than this. So I'm not going to bother to do it. These systems have the case when the difference between the decays is exponentially distributed systems have been studied a long time ago. They're called Mark-jump linear systems. In Mark-jump linear systems, often you didn't have the resets, but that doesn't really change much. It's a very nice case because in that case, X turns out to be a Markov process. Because when you have exponentially distributed amount of time, you have this memoryless property. You don't have to remember when you got into a mode. All right. And there was a very well-developed theory for stability, optimal control, etc. But, as I told you before, for network control systems, you never have exponential stability, at least in any reasonable way. OK, let's not worry about that for now. If I wanted to model then the system through a stochastic hybrid system, what I do is I actually only need two modes. The dynamics are actually the same in both nodes. The only reason I need two modes is we'll have to do these reset maps, because different things happen whether you are at an even or odd instant of time, right? So I have to worry about that. The A that you see here is just the open loop dynamics, because in between sending measurements, you just have a constant input here to the controller. Well, in general, the system is not. You're trying to stabilize it. So in fact, keep in mind that this is typically not stable unless your system was stable to start with. So you have to worry about having an unstable system running. What's going to stabilize the system is going to be actually the jumps. It's going to be the fact that whenever I send a message, and at the odd instant of times I'm sending Y1, you have to update these Y1s. These J's, and you need different J's to encounter this, are going to actually be the stabilizing factors in that system. Right? Yeah?
Are you assuming that sensor 2 is monitoring the sensor 1 transmission, so it won't try to send again until it knows that sensor 1 got its message through?
Yes. Okay. In this particular model, I am. Because they are this round-robin thing. Yes, I am. There would have, I mean, in something like the CAN bus, it would be rather straightforward because everybody can listen to the bus. You know exactly who transmitted. In a wireless case, it would be more complicated. It turns out that even when the general case for general distributions, stability of these systems is easy to test. There are necessary and sufficient conditions for stability. I'm going to show you what they look like. They end up being linear matrix inequalities. Let me just show you what the sufficiency of the conditions is actually easy to understand. The necessity is more complicated. But I simplified my life here to keep the notation simple. Instead of having two modes jumping between the two, imagine that you just have one sensor. If you had one sensor, there's just one jump. Right? This is what I'm going to say would generalize for the case of two sensors, but I'd have to keep track of. I'd have more indices. So I'm just going to say a system like that. X dot equals AX. Typically, that A may be unstable. And occasionally, I send measurements, and that causes. By the way, the only piece of that state that changes is the hold. Right? Because the state of my process, the state here, that you have here is the state of the process, the state of the control, and the state of the hold. Nothing happens to the state of process or the control. It's just the hold. That's the only thing that changes there. OK. So what I'm going to do is, this is not equal samples time, but let me just define x sub k to be x at time tk. If I have that, writing my xk plus 1 as a function of x sub k is straightforward. It's a linear system. It's matrix exponential, and then the reset afterwards. All right? So this will be the state just after a reset, to figure out the next one, evolve the system, jump, etc. The caveat, of course, is that this is a random variable. Right? It's tk. I know the distribution. It's what I'm calling f, the cumulative distribution. OK, so one thing I could do is this. Let's take a matrix and figure out what would be the expected value of a quadratic form at the next instant of time, given my current instant of time. That's straightforward to do. All I need to do is to plug in that formula, and this is what you get. The expectation that you're going to get here, see, I'm given the state. So this is given now. The only randomness here is in this guy, which has a particular distribution. So this is what you get. Now, let's suppose that we're so lucky that when I take this expected value, this now is it's a matrix. I could compute it. Suppose that you are so lucky that that expected value turned out to be small or equal, in the sense that the difference is negative semi-definite. Then a number, let's say 1/2 times the matrix P itself. Right? Well, in that case, here I just get gamma P. I get this, so I get this expression. And if I were to take expected values on both sides with respect to x, I get this expression. It's a wonderful expression, because it tells me that the quadratic form, the expected value of quadratic form, is converging exponentially fast to 0. Because every time I go to next time, I just multiply by a smaller constant. It turns out, so what I've just shown you here is that if I could find a matrix P so that that expectation is smaller than P, also in the sense of negative semi-definite, then I could conclude that the expected value of x squared, because I was assuming this is positive definite, so that gives me the norm also, would converge to 0 exponentially fast. Fast with respect to the index k, not necessarily with respect to time. There's two questions here. One is, do I have to worry about what happens to x between the jumps? Question number one. Second is, am I just being overly optimistic? Maybe such a P does not exist, and yet I still have stability. Well, it turns out that, in fact, this is almost a necessary and sufficient condition for stability. Let me just guide you through this. So the necessary and sufficient condition to have mean square exponential stability, there's two things that are needed. There's an equivalence here, so in fact it's going to be necessary and sufficient. What you've seen here is what I've shown you before. That's the condition to make sure that at sample time things converge to 0. But there's another condition here. It looks a bit messy. Let me tell you a few cases where you don't have to worry about it. When A is stable, this is always true. The other case when it's always true is when the support of your distribution is finite. This condition actually is only about the intersampling time. Is to make sure that between samples nothing bad happens. If the matrix A is stable, nothing could ever go bad between samples. If the support of the distribution is finite, nothing could go bad. At most, you grow exponentially for a finite of time. You only have to worry when the support is infinite. So there's always a possibility it's going to grow arbitrarily large. And then you have to worry about how the tail of the distribution compares to the exponential rate of the system. And what is condition? This is the tail of the distribution. This is how bad the exponential matrix has to go. And if you want to have exponential stability, this product has to go to 0 exponentially fast. So that's just to worry about intersampling behavior. And it turns out that when you put these two, this is the necessary and sufficient condition. If you were interested in other forms of stability, for example, I was putting exponentially fast. Actually, the only difference is that if you put here, if you don't care about exponentially fast, you also don't put it there. So this, you can actually generalize this for all sorts of conditions. This is actually just a condition on the comparison of the eigenvalues, n stable eigenvalues of A and the tail of distribution. Very simple to test. This is just a matrix inequality, an LMI. It's linear on P. You have to do some integration here, but it's integration over one variable, time. This is trivial to do numerically. So in fact, you get a necessary and sufficient condition for a system like that, the one I've shown you before. there's lots of things that can be generalized here. You could put multiple modes. You could put the interval between consecutive samples not to be the same on every mode. You need a few more LMIs. You could also put, well, that's actually always the same. You could also, there's situations where you, especially if you're looking at wireless communications, when you get into these deep fading modes, then the probability of having a drop somehow increases. You can also encode that. Okay, so there's lots of variations on this. For all of them, there's necessary and sufficient conditions, which all come in forms of LMIs. Things I did not talk about here. There is very interesting work, perhaps even more interesting, to do when you have different forms of stochasticity. I showed you something very simple, which is stochasticity only have to do. It may depend on the discrete state, but I wasn't allowing to depend on the continuous state. Right? This type of system you see here, that lambda 1 of x dt, the way to read that is, when I'm at a certain state x, and I want to ask, what's the probability I'm going to have that transition in a small interval from the current time to t plus dt, where dt converges to 0? Well, in general, it's going to be proportional to dt, the length of the interval, and that constant proportionality is called the intensity. And you can make that depend on the continuous state. These are much more difficult systems. For these ones, there are no simple results of necessary and sufficient conditions for stability, but there are Lyapunov-based methods to say stability. And to be honest, as far as research goes, this is the next place to go. I could say a few more things, but I want to have time for the second part of my talk, so I'm going to jump right into that. So most of this was about communication and what happens when you have control loops with networks in the middle. I want to now explore a little bit computation. And so I'm going to tell you about a particular control design method that makes use of a lot of computation. So what I'm going to talk about is actually something called an integration of model predictive control, the moving horizon estimation, which is, you'll see what that is. But let me just start with model predictive control. So the idea behind model predictive control is this. You have a system, xt plus 1 equals f of t of x, f of x of t, u of t. And you are at a particular point in time, and you construct a cost which sort of provides you an objective for what you'd like to happen between now and some time capital T in the future. Right? You're going to do planning for, next 10 seconds. You have some idea of what you want. That's called the running cost. And you have maybe some cost because maybe I want to finish at a particular, after these 10 seconds, I want to be in a particular place. And then you are at a certain time t. You solve this optimization. And this gives you a control that you're going to use from now throughout all 10 seconds. So you compute all these things from now to 10 seconds. Then you take the first one. You apply that, maybe just for a millisecond. And then you get a new measurement, and you repeat this optimization. You keep doing this. So the caveat is, every maybe millisecond, you have to solve this optimization. Okay? Why is this? This is a very popular way of doing control. I'll tell you why. So there's, assuming that you are OK with solving nonlinear optimization problems, and you're able to solve them, let's say, in a few milliseconds, then you're able to, in this optimization, put constraints. You could put the constraints. Maybe I want my u to be between -1 and 1. Maybe I want my x to avoid a particular area of the state space I don't like, etc. You directly address performance, right? You put there. In principle, once again, if you're willing to solve nonlinear programs, it could be a nonlinear system. A couple of problems here. One is, in practice, although you plan for, let's say, 1 second, you're actually never going to fully execute that plan in principle. So even if this optimization gave you a good result, because you're always changing, it could actually not converge at all. So you have to worry about whether or not this works. So that falls in establishing stability. The other one is that the idea is, for this to work, the way it's done here, is that you're going to do a prediction from now to, let's say, 1 second into the future. You need to know what now means. What is the current state? So that can predict I go through my dynamics, I figure out what's going to happen in the next second. So this actually means full state measurements. And then, of course, there's, if you want to solve this in 1 millisecond, you have to be able to do that, solve these things very fast. The first thing I want to address, and that's the stuff, one of the things we've done, is to address the full state measurement. So one thing you can do is, well, let's just do some sort of filter, a state estimator. Maybe design an observer. But we have all this computation power, so why not also think of it from a numerical perspective? And this had been done before. There's something called moving horizon estimation. The idea is the following. Now, imagine I'm just trying to estimate the state. Moving horizon estimation actually is just basically solving a maximum likelihood problem, numerically. So what I do is I have a process there which had some control U, disturbance D, and I forgot there should be some output equation which has some measurement N. So let me write down what that equation perhaps looked like, because I forgot it there. So something like yt is equal to some nonlinear function of the state plus noise. And what I do is I collected measurements over a certain interval of time in the past. Goes from now, let's say, to the last 1 second. I got a bunch of measurements. I don't know what was my past disturbances, my past noise, and I don't know what my initial condition was. All right? But I could certainly write a log likelihood of those. Keep those as variables. All these things you don't know, disturbance, noise, keep those as variables. Write the log likelihood of that for the whole sequence of past measurements, noise, and state. And then, so for an optimization, we're going to maximize the likelihood subject to the measurements that you collected. So it's just maximum likelihood estimation, but now doing it numerically. Okay? Of course, the events are sort of the same. In principle, if I'm willing to solve nonlinear programs, then I could do this for nonlinear processes. I don't need to worry, don't need to make simplifying assumptions, like assuming that my noise is Gaussian, etc. I could put constraints. Maybe I know for sure that, for example, my state can never be negative. It's a population, for example. So in principle, I can put all the constraints I want. And in fact, that's the reason why this is also very popular, mostly in the chemical process industry, because very often you have constraints on the state that you know. Okay. I'm going to try to combine these two. Let me show you how I'm going to do this. Oh, I should write here. In practice, what this thing looks like, if your disturbances and noise are independent from time to time, when you write down what the log likelihood looks like, it's going to be something like this. Because I want a maximum, yeah. So I put here the symmetric of the log likelihood. So basically think of these as the logs of the PDFs of N and D, and this is what the log likelihood is. You get summations because I was assuming that they are independent of cross time, so you multiply them when you take logs, these summations. Look like this. So these are the problem I'm going to solve instead. I'm going to try to combine model predictive control with estimation. There's going to be two pieces to my cost function. One which has to do with the control part. Basically, this part is about promoting a good performance. I'm going to try to minimize the criteria, very much like the type of criteria I see in model predictive control. And then I add a term which basically is going to penalize unlikely values for my disturbance and noise. All right? That's one piece of the puzzle. The other is that what I'm going to solve is a problem like this. I'm going to minimize the control signal, meaning I want to get the best possible performance. These are the costs I want to minimize. But for worst case assumptions on all the variables I don't know, my state on the past, and my disturbance and noise. But remember that although I'm putting a max here, I'm penalizing unlikely things. There's another picture here which is sort of useful to figure out how this works in practice. So imagine that you are at a certain time t. Right? I'm here. I know what were the past control inputs, and I know my past measurements. The future I don't know. I'm trying to predict the future, right? I'm trying to figure out what. So in the problem that you see there, that min-max problem, there's some things that appear as parameters. My past outputs, and these are my measurements, and my past inputs, they are parameters to my optimization. as I go from one time to the next, those parameters will change because I get new measurements. The optimization variables are going to be lots of them. The controls, the future controls, the past controls, there's nothing I can do about them. Future disturbances, because I want to think about what my opponent may do in the future. But I also don't know the past disturbances. Those are also optimization variables. So both past and future disturbances. The initial state, and I forgot one, the past noise, right? Because I also don't know what these ends are. In practice, these ends are not going to be optimization variables. That's the reason they're not there, because n is just y minus g. So in fact, they are completely determined by that equation. I don't need to worry about them. That's why I think I forgot them there. So now there's a question, which is, why do I want to integrate the control part with the estimation? And there's a good reason not to do it, is that solving a large optimization is worse than solving two small optimizations, right? So by integrating this, in principle, and I'll argue that's not always the case, but in principle, computationally, this is worse. Unless you have a problem that scales linearly with the number of variables, it's better to solve two small optimizations than a large optimization. OK, but why to do it? I'll go back to the same question. If you're just a theoretician, and sometimes I put that hat, actually, we are able to prove that this algorithm leads to stability. But even if you're a practical person, in practice this works well, and probably the two things are not decoupled. Because the issue when you solve that optimization is that in your choice of control, you're taking into account the worst possible disturbance that could come. So in fact, your control is assuming worst case disturbances. So when the real disturbance and noise comes, you are prepared for those. So you don't follow the risk of being overly optimistic. I could say a little bit more about this, but I'm not going to do that. I want to have time to tell you a few more things. By the way, notice that although we're solving a min-max problem, and one always has to worry about being overly conservative, those penalty terms on unlikely disturbance allows us not to be conservative. In fact, I can penalize those things tremendously, basically not giving any power to disturbance and noise. Those are tuning parameters for my controller design. I have some slides here on what is needed to make this work. Not going to dwell too much time on those. There's basically three assumptions that you need for this. Two of them, you'd expect them. One is, this is only going to work if your system is controllable. Okay. It comes from an assumption. This particular assumption has to do with the existence of an ISS controller Punov function. If you've seen model predictive control, it's an assumption that always appears in model predictive control. There's a few alternatives that you could use here. The second one, which has not appeared so much before in this sense, basically your system has to be observable. You have to observe enough of the state to be able to predict it using your past horizon. It's stated here in a convoluted way because we are doing this in completely general for nonlinear systems. If this was a linear system, I could just write here the pair CA is observable, but I can't. And I'm running a little bit out of time, so I'm not going to do that. The third assumption, it's interesting, and in fact, it's going to be important for multiple things. We're going to require that min and max commute. So this is actually, it's going to be what's called a saddle point. Okay. We understand this assumption much less than the other two. The other two you'd expect. You'd be surprised if they weren't there. I can tell you a few things about it. Well, from very general results, if this function is convex in U and concave on the values you're maximizing, then this would be min and max commute. For linear systems and quadratic costs, we can figure out what this means. It is an observability assumption. It's a little bit more tricky than that. The system has to be observable, and you have to select this row and n's. You have to penalize them. You couldn't put them 0. You have to put them some numbers. And it is more or less easy to see. I mean, if you don't penalize the disturbance and noise, and this max really has nothing will keep it small. For nonlinear systems, we don't have a condition. What we know from trying out with the examples is that still you have to penalize these things. There's a stability proof. I'm not going to worry about that. This other assumption has another important thing here. This assumption actually going to allow us to solve this fairly efficiently. Very general result on saddle points is that the min and max commute are equivalent to the existence of a triple in this case, such that if I plug in some optimal d and n, and I do a min with respect to u, I get a value. But if instead I plug in the optimal u and now do a minimization with respect to n and d, I get the same value. So if an oracle would give me the d and the n, then it's finding the u would be trivial. I just do this minimization, vice versa. Well, I have no oracle, but this is not really very problematic. Imagine, for example, for a start, that I have everything is smooth, no constraints. Well, this would just mean that the derivative of j with respect to u at the optimal is going to be equal to 0, and these two. Well, in that case, I just have two systems of nonlinear equations, and these are all unknowns. I could use Newton's method to solve that. If I have constraints, actually the problem is not much more complicated. What you're going to do in that case is write down the KKT conditions for this system, which are going to appear as a function of d star, n star, and u star. Write down the KKT conditions, optimal conditions for that system. So now you get two sets of conditions, apply Newton's method and solve it. And in fact, that's what we do. We do some standard tricks. Actually, we use an interior point method to do this, but it's fairly standard stuff. This works incredibly well. This is a simple system. It's a linear system, quadratic cost, a flexible beam. Look at the solution times for this system. So about hundreds of optimizations, hundreds of constraints, 3 milliseconds. That's how long it takes. So we can control the system easily at, let's say, 300 hertz, if what you want. And by the way, it's interesting when you do these problems because you do the planning for a longer horizon. If one optimization fails, it doesn't matter because you can still use the values from the previous optimization. But this was easy because this was concave-convex. So let me show you another example. It's a pursuit evasion game. You have the evader is sort of a double integrator. It goes a little slower, but can move in any direction. The pursuer is a Dubin's vehicle. So you control basically the angle, but you have constant velocity. A little bit more large number of equations. But this is definitely not convex because what's going to happen is here are the trajectories. So when you're chasing something that's slower than you, you're faster, so you can go to the left or to the right. There's always a symmetry there, but not in between. So this shows you that this is not a convex problem. In fact, you see the trajectory. This still is just a few milliseconds. Newton's method is really, really powerful. We actually had some experiments there. I don't matter. We can even do things like put wind. So what we did in this simulation was we took the wind to be an extra piece of your state. We assumed wind to be constant. We just put the wind direction derivative is equal to 0. Take that as part of the state, solve this problem. In fact, what happens is you find some pursuit policies that also estimate the direction of the wind and compensate for that. By the way, I should have said this when I told you the solution times, 3-4 milliseconds. This was on a laptop. If you do this on a Raspberry Pi, just multiply by 3, something like that, because the clock is slower. But still, when you solve these systems, typically UAV you can control it at 10 hertz, so we have lots of time. Okay, so this is basically the end. Two things I didn't talk about, but it would be interesting. One of them is if you really want to use a microcontroller to do some of these systems, then it's not going to be milliseconds. That's going to be slower than that. But there are ways to do that. One of them is to do some computation online and some computation offline. And that's some interesting stuff to be done. The other one, though, is that when you start introducing process and smart process in the systems, then you open the door for something to hack into these systems, right? You introduce smartness. Smartness allows you to do stuff, but allows someone else to also fool your system. So in that particular area, I think the interesting message is to try to build control loops which can be robust with respect to attacks. Perhaps using the kind of things I've shown you here, where you do maximization over actions against you. And the problems are not easy, but there's a few interesting results there. And I think this is the end. Thank you. The thank is hidden there.
We have time for like one or two questions.
Sorry. Yes?
So how would you, if you would actually do a distributed control algorithm on the different sensors, where you actually do processing on the sensor nodes, how would that partitioning work? Because there's such an asymmetry of the processing powers between the microcontroller and the central computer.
This stuff here.
Yeah.
What I had there in mind was a different thing. I'll get to your question, but let me just clarify this was not what I meant here. What I meant here is that you can do a lot of these computations, do it previously. You can spend a lot of time. I mean, I'll give you something, it's not a good idea, but conceptually would work. Imagine that I just grid all my state space and offline solve an optimization for every position of the state space. Then the vehicle only has to have a lookup table, right?
Yeah,
So,
the devices aren't only processed, like they're not only constrained by processing power, but they're also highly memory constrained.
but memory is much cheaper than processing power because think if it's a table, it's not RAM.
Yeah, but
It could be you could easily connect to an SD card.
the quantum microcontroller also goes up with flash.
It could be. I mean, it could be. You know, when I think of something like an Arduino or something like that, I think about 1 kilobyte of RAM, but 128 kilobytes of programming memory. Now, going back to your question, one thing that you can also do here is to simplify the life of the controller by asking it to solve online a simple problem, right? And then have some offline computation. So imagine that I want to, let's use the Amazon problem. Imagine I want to deliver a package to my home. You can imagine someone on the cloud doing a computing an optimal path, and just sending to the UAV what you need to do over a small horizon of time. Now the UAV then figures out, well, I lost a little bit of altitude, now I have to do this, I see an obstacle. So you get a small problem to be solved, but they have someone else at a higher level just sort of giving higher level controls. So that's closer perhaps to what you're asking.
Question about your objection?
Yes.
The second term is the penalty for bad things.
Yes, for unlikely
So
things.
if there's a bad noise or disturbance, highly unlikely,
Mm-hmm.
then essentially I ignore it.
So
The likelihood will be very small.
yes. So if you sorry, this is not the right form. Yeah, it's just as a minus sign, so it was confusing.
So that disturbance term, I mean, the noise we can predict.
Yes.
Disturbance term is highly unlikely, but very bad.
Yes.
This would ignore it.
Depending on how you weight it here, yes. But if it would be very, very unlikely, essentially, yes. It will be ignored because it would put such a high penalty here that this
So this is
maximize it.
likelihood.
Generally, what we do, we put here sort of likelihood terms, yes.
So if it's a likelihood, then it's very small likelihood.
Yes. So it's going to be a very large row because this is the log and the negative of it. So it's very unlikely it's going to be a very negative thing.
Yes, so your objective is...
So, but you're right. It's going to be this maximum is going to just ignore it. Yes.
So it's not conservative in that sense.
Yes. Yes. It's not considered in that
If
sense.
I wanted consonants or something.
Then you play with this.
Then play with that.
You play with that, right? Although I think of this as a likely term,
Yeah.
you know, there's no stochastic interpretation of this in this formulation. So, in practice, you know, we start with things that come out of what we believe the noise is, but if we don't like the trajectories, we'll play with it until it wears out.
And in the 2 slides before this.
Mm-hmm. Maybe more?
Yeah, so here you're saying that like this protect feedback against potentially optimistic state estimates. Actually, doesn't this encourage like optimistic state estimates?
I'll tell you what I mean by this. I add more to say here. When you separate the two problems, you get measurements, and there is no, this idea of having a point estimate is sort of an abstraction, right? You just typically get some interval, either you characterize stochastically or not. When you solve the two problems, your observer doesn't know how to choose among all those possibilities, right? Maybe it's going to give you a point estimate. Maybe something very sophisticated will give you a point estimate, perhaps a covariance matrix. If it does that, then it's good. Perhaps the controller can take advantage of that. But more often than not, it gives you a point estimate. So then the controller is going to pick a U, forgetting the fact that you actually have information telling you that even though I gave you a point estimate, maybe my state is always here, and maybe this would be a terrible place to be. And so even though this piece is just as likely as this one, if my picture had been symmetric, from the perspective generated the control signal, I'm going to protect myself against this because this could lead me to trouble. This is more noticeable in problems where there's asymmetries. So one example that we did was a problem of diabetes control, this artificial pancreas. And in that case, I think undershoots are much worse than overshoots. And so what we'd see there is that this particular control would sort of, well, I know I'm equally likely to be in all this interval, but I really don't want to do the undershoot, I think. And so I'm going to sort of shoot a little bit above. So there we would see very clearly, in that case, a reduction of undershoots. So when you put these two together, you reason about the uncertainty when you generate the control, which generally is not the case when you separate the two.
So going back, maybe your first line, you don't have to put it up.
Mm-hmm.
You know, there is this thesis that computation is getting cheap, which it is. Bandwidth is cheap, memory is cheap. What is the bottleneck that is preventing more and more a greater proliferation? Like if I look at airplanes, you know, a lot of it fly-by-wire. Their bandwidth bottleneck is in the entertainment system, not in the control system. You know, and of course you prioritize control over whatever video passengers are watching. But are control applications gated by technological? What are they gated by?
I mean, so
uncertainty in the environment,
let's say,
by modeling?
now they may still be gated by algorithms. So, I mean, a lot of things we have computations, but eventually there's fundamental limitations you can't do much about. If you have a system, it's unstable, and you have a lot of delay in your communication. Delay, right? Delay is limited by speed of light. No matter how fast you go, at some point you can't go. You are going to have a problem. Maybe not instability, delay. No matter what delay is, you always be able to stabilize the system. But performance is a different story. If I cannot react faster than a certain amount of time, there's nothing I can do about it. Right? But we're still a little bit far from speed of light. Well, having said this, that's actually not true. The reason why that CAN bus is limited at 1 megabit per second is because of the speed of light. The way that bus works is that when someone writes on the bus on one side of the car, every device has to read the same bit. And so they figured out that for 40-meter bus, you cannot do more than 1 megabit
CAN
per
bus
second.
seems to be obsolete.
Yeah, it's an obsolete thing, exactly.
And yeah, it's still used in every car.
Yeah, and yeah.
And still used in every car on the road without any security.
Yeah.
I would have
Still obsolete.
It's still obsolete.
I would have thought that in modeling the uncertain environment in which these autonomous devices, whether it's cars, you have to worry about pedestrians, you worry about other cars, that the safety critical things when you have an enormously complicated environment is probably what is that is a big. I mean, I don't work in this, but I work in a regulated environment in my office.
But I mean, some of those things you can alleviate by just putting more sensors. I mean, maybe you don't want to do that, but sensors are getting very cheap. So
there's also technology that gives you more guarantees, like user CAD, that actually gives you a 100% guarantee.
Like what? Sorry, I couldn't.
User CAD. It's
Okay. Okay.
Some companies developed it 10 years ago, and they actually have some hard real-time guarantees that they give you that you correctly can't really do that because you would have to make assumptions that are true anymore.
If you have any more questions, we can ask the speaker offline.
All right.